Einstein formulated his special theory of relativity in 1905 and published his general theory of relativity in 1916. And general theory of relativity is mostly considered with gravity, and the special theory of relativity was mostly considered with mostly light. The speed of light was the problem that was solved with the special theory of relativity. So let's go back to ancient times. And in ancient times, the ancient people looked at falling objects like apples falling to the ground or anything that they thought that was natural. There's nothing to question. That's the way it is. And people did not question anything. The very first person to question and start thinking about gravity was Isaac Newton. And he thought, and he came up with an equation. F equals G is the gravitational constant. M1 is the mass of one object. Here we have Earth and the Sun. So M1 is the mass of one of the objects. M2 is the mass of the other object. R is the distance between the two objects, and R squared. And the force between the two objects would be given by G times M1 times M2 divided by R squared. So this was the first time that somebody came up with an equation for gravity. And this equation was used by Johannes Kepler. And he formulated a bunch of other equations, which we are not going to go into here. And those equations, based on Newton's, this equation, F equals G times M1 M2 R squared. And Johannes Kepler built on that, and he was able to predict the path of planets around the sun. So the solar system movements can be predicted using Kepler's laws, but the Kepler's laws were based on Newton's equations. So if you go here, now as we all know, the Earth goes around the sun in an ellipse. Now circle has a one center, but mathematically speaking, ellipse has two centers. One is called the perihelion and the other one is called the aphelion. So now the sun is at the perihelion, and the other one is, there's nothing there. It's just a mathematical point. So I just showed the ellipse and two points. One is the perihelion and the other one is the aphelion. So the Earth goes around in an ellipse like that. Actually the ellipse is not this pronounced, but it's still an ellipse. Earth does not go around the sun in a circle. It goes around in an ellipse. So then what happened? So when the telescopes became more powerful, better and better data was obtained. Astronomers found that the location of the perihelion, I cannot see this here, the location of the perihelion, here we go back here, this is the perihelion. When it goes around, the perihelion is the location of the sun, and this location of the sun with relative to Mercury, it happened with the Mercury, the location of the sun is shown here. And this location, every revolution, after every revolution, this location would change slightly. That is the change in the perihelion of Mercury. So
what
understand?
Revolution?
Like every time the Mercury goes around the sun, the perihelion, the sun is at a perihelion, right? The sun is at a perihelion. So first time it goes around, fine, it's here. But the second time it goes around, the distance between the Mercury and the sun has changed a little bit. So the perihelion has changed a little bit.
And that's called a revolution?
Yeah, one cycle is called a revolution. One is one revolution.
Okay.
So every time it goes around, this distance between the sun and the Mercury has changed a little bit. Not a whole lot. It happens to all the planets, but it's more measurable in the case of Mercury. All right. So this change in the location of the sun with relative to Mercury after every orbital cycle cannot be explained using Kepler's laws. So the Kepler's laws cannot explain this change in the location of the sun after every orbital cycle of the planet. So this was a problem. So this problem was, people started looking, this happened, this was identified in 1880s, like 20-30 years before Einstein solved this problem. So this problem was not solved until Einstein came along, because Kepler's laws were based on Newton's law, and they look,
nothing changes in that
right,
equation. Nothing changes.
Right. The equations does not show anything why this location of the sun after every cycle has to change. Mm-hmm. Kepler's equation does not show that. So the Kepler's equation, when they look at it, they were fine. There's nothing wrong with this Kepler's equation. Then it was obvious that something wrong with the Newton's equation, this equation, because Kepler's equations are based on this equation. The gravity was considered to be a force
but
by
doesn't
Newton.
Gravity change in different places of the space?
Well, it changes because, like, if the Earth is here, then the gravity, according to Newton, would change if you change the location. If you change R, then R would increase and the F would go down.
Okay.
Right? So if the location is not changed, then the gravity would be, the force would be the same. Because this G will not change. That will not change. And the M1 and M2 are the masses. They will not change unless it changes like a little bit, like if some meteor falls or something, but that's not much. So, but this equation has to be wrong, because these equations were more concrete, like they were not fluid, to explain this change in the location of the sun after every revolution of the planet. So now there were other problems. So this is a problem, right? This is a problem, unsolved problem. Like today we don't know what happened before the Big Bang, that kind of problem, right?
I think we should pause, do the first part until the 8, because the 9th slide